Okay, good morning and good afternoon, everyone, wherever you happen to be logging in from. Welcome to the Storage Trends in AI. We'll give the audience another 30 seconds or so to get situated, and then we'll get started. Okay. We'll go ahead and get started here today. Hello again, everyone. Thank you, and welcome to the Storage Trends in AI. I'm Jeremiah Tussey, the MC of sorts for today's discussion. As artificial intelligence continues to transform in industries and the demands on storage systems are evolving at an unprecedented pace. Today, I'm joined by two industry experts where together we will explore the trends and technology shaping the future of storage in an AI-driven world and how organizations can prepare for these changes. Our first expert guest is Patrick Kennedy of ServeTheHome. Patrick, if you could introduce yourself and give us a little background.
Awesome. Hey guys, this is Patrick from ServeTheHome. I started at ServeTheHome in 2009, and we have been doing server reviews for well over a decade now. We actually have some 8 GPU AI server reviews that are now around a decade old on the site, which is always kind of fun. And we've been able to go and look at some of the large installations that are out there, both actually installed, but also some of the new bits of technology that are making their way into the market these days. So anyway, that's me. You may know me from the website, YouTube channel, and if not, you should definitely go check those out.
Great, thank you, Patrick. And our next expert guest is Jay Metz, Dr. J, Chair of SNIA. You may know him as Dr. J, so I'll let you introduce yourself.
Or you may not know me as Dr. J. Either way, it's a possibility. So my name is Jay Metz. I am the chair of SNIA, and I'm very happy to be here on this conversation because, as I've often mentioned, storage is my passion and my bane of my existence. So I'm always enjoying being able to have a chat about this conversation.
All right, great, thank you. And to round out this crew, I am Jeremiah Tussey. I'm a product marketing manager of SAS SATA NVMe Storage Controller Silicon and SAS Expander products in the Data Center Solutions microchip technologies. I'm also an alliance manager for the Data Center Solutions. I'm here today as a board member at large for the SCSI Trade Association community with SNIA. I have over 25 years of experience in storage, starting back at SCSI Fiber Channel, then transitioning to SAS and SATA, and ultimately PCIe and NVMe. Today, we are going to look at the storage trends in AI, and sponsored by the SCSI Trade Association. Just a little bit of word there. SCSI Trade Association themselves promotes the understanding and use of serial attached SCSI and all things SCSI, and the SCSI standards to meet future industry needs. So we'll first kick off with a SNIA legal notice. This is shared on every webinar for reference. I'll leave this here for just a moment for the viewers. And a little bit of housekeeping. For this webinar, please ask questions in the dialog box on your screen. Questions will be answered at the end of the webinar. If we don't get to your question today, we will post a follow-up blog to answer it. And slides are available for download via the SNIA Educational Library. Polls will be presented and participation is highly encouraged. So we appreciate that. Thank you. So to kick this off, we wanted to start with a polling question. What is the biggest challenge when it comes to AI storage? So I'll go ahead and kick off that poll. Overall, we're looking at a couple of different responses here: managing data volume or data security, impact on workload performance or cost and ROI? So which of these are your biggest challenge when it comes to AI storage? Okay. Give it a few more moments. Okay. Looks like we've got a good polling so far. It looks like the number one item is impact on workload performance, followed by data security. That is also, an increasingly important aspect for sure with new requirements coming in. Then managing the data volume is number 3, followed by, and last but not least, cost and ROI. So Jay, what are your thoughts on the biggest challenge for AI storage?
I agree with the stacking of this particular poll. As a matter of fact, I mean, as we're going to see a little bit later on, there's a lot of nuances that go on with this, and when you're talking about doing AI, you're first and foremost looking at a specific type of workload. And like I said, we'll get to some of the specifics a little later on. But that workload is demanding. It's like trying to do Formula One racing. What's your first thing? Is it probably not cost and ROI for Formula One racing? It's to win the race. And AI is one of those things that's kind of a souped up version of what your data center what your storage would normally do. So it's a different type of need. It's not to say that costs and ROI or security aren't important, because they are. They're very, very important. You don't want to pay for things that you don't have to. But the nature of the work itself, the nature of the beast itself, means that the ultimate priority of what you're looking to do is get the job done. So I think that this is probably a good reflection of the actual needs that I've seen in my journey. Patrick, what do you think?
Yeah, excellent. Yeah, Patrick, what are your thoughts?
Yeah, I think I'd definitely be. I see the ranking has changed a little bit over the last couple seconds, but I'd say that this feels like a pretty good ranking. The performance aspect, I think, is fascinating when we start getting into that, which I think we'll talk about it a little bit later. But I think certainly just the amount of data you have, and also the cost and ROI. Everybody has challenges when it comes to how much these large installations are cost, as well as even just some of the smaller ones. So I think that's definitely it. And the data security is definitely going to become a bigger concern going forward, and we're already starting to see a little bit of that. So,
okay, yeah, and just as an update too, it seems like impact on workload performance is by far the number one, and there's almost a three-way tie with the others: managing data volume, data security, and the cost and ROI. So, good input there. So why don't we get on to some of the details of today's discussion: storage architecture. So when we look at storage architecture, we from the SCSI Trade Association take a look at our SCSI Trade Association serial attached SCSI technology roadmap. The AI workloads are evolving rapidly, placing demand on high performance, scalability, and reliability from a storage infrastructure standpoint. So SAS is viewed as a tried and true technology in general that can be leveraged in various architectures in AI. So here, as the SAS technology roadmap shows, there has been a long history of innovation to service various storage demands. And 24 gig SAS has been shipping for a number of years now itself. We just completed a third Plug Fest last year, which was quite a successful event, and had a big setup with end-to-end 24 gig SAS operating in the architecture. So it was a good culmination of all the efforts that have been happening over the last few years. Today, our focus is on 24G Plus SaaS, which is a culmination of several already defined features and options, as highlighted here, as well as the consideration for additional capabilities to align with new system requirements. So digging a little bit deeper here as we look at serial attached SCSI and how it plays a key role in AI storage architecture. This goes hand in hand with key features and the roadmap of SaaS to address the evolving needs of AI. So without getting into too much detail here, this is kind of an overall list of what's going on currently and already defined, where the already defined features are being pushed for further improvement on the efficiencies in SaaS storage architectures, and some are related to media and connectivity-based enhancements to improve serviceability and manageability of the holistic storage. While the newer proposals are more along the lines of enhancing security, supporting larger capacity, data reliability, and quality of service across the system. So overall, these features collectively are addressing storage requirements that benefit AI implementations. So as we look at the phases of AI and storage workload requirements, most customers feel confident in using existing infrastructure today, although things are evolving on that front. The GPU is an accelerator for the storage on the back end in the majority of the cases, and storage over time will evolve and become more efficient to address the various needs in these different phases and the various workload requirements. AI workloads interact within the storage at every stage of the AI data processing, but to drill into some of the storage intercepts with these different phases, we look into the ingest phase, which is mainly where you're collecting and using massive amounts of structured or unstructured data in a local or disaggregated form. This raw data is the data sets that require a large scalability factor and tends to have a lot of rapid growth, mixed data sizes. So a lot of dynamics on that side of the data collection and data usage model. So predominantly this area is hard drive based storage, where storage data may already exist in existing systems in a cold or warm fashion, or maybe even in the implementation of some capacity based SSD architectures. Hard drive capacity storage is the best dollars per terabyte generally today when you look at the raw data, with SAS and SATA hard drives being the main infrastructure supported. SAS architecture with probably dominantly SATA hard drives is probably the main implementation for ingest. Now, when we transform this data, we look at requiring a level of high sequential writes, throughputs, and random reads collectively. So you start seeing a hybrid architecture start to evolve here, where you have a need for formatting and evaluating the data, annotating the data. So here you'll likely see a mixture of SAS SATA hard drives, probably about 70 to 80% of your architecture, while on the higher end in a caching form, you would see SSDs implemented or an all-flash array, whether it's SAS, SATA, or NVMe in that case. So this is more of a warm, hot type of architecture is what's expected in this level of the transformation of the AI model. And as we evolve to the training and tuning process, the requirements start to accelerate to a higher demand on the storage processing, where you'll end up in a processing and evaluation loop with periodic checkpoints that need to save and reload the data. So you're having a loop of this going on and on and on until you get to a trained model. And this is more where you implement your performance storage, specifically NVMe and SAS SSDs or all-flash arrays at this front end of the architecture. GPU direct access to NVMe storage is a key element here in some of the models, where you're doing direct data analysis, generative AI, predictive artificial intelligence, and machine learning on the data to bring it to your inference stage. So at your inference stage, you finally have your model deployment, and where you're reading the model and have your data structured in a way that you're most efficient. And so you're basically just feeding those GPUs, and it's a feedback loop as you get input to that data. So that's kind of at a high level where we see the different types of technologies intercepting the different phases of the AI. So I guess a quick question, since we've highlighted how SAS supports both the high performance and the scalable storage performance, scalable storage portions of AI, Patrick, what would you see as a mix of fast storage or active data and cost-effective capacity storage deployments? And are you seeing tiered environments being used more frequently in AI architectures?
Yeah, so we'll go into this in a little bit. Also, just kind of have some slides on this, but the real thing that we're seeing these days is we're seeing folks predominantly in AI clusters deploy in a pretty uniform way in the nodes. So if you're talking about in nodes, you're going to have NVMe storage, and that's just kind of the way it is, just because of the performance requirements and latency requirements. Then once you kind of get to cluster storage, there are two real ways that folks are deploying. One, they're deploying primarily, all NVMe, high capacity NVMe usually, or the other way that they're looking at it is really doing more of more doing a tiered approach where you have an NVMe kind of fast layer, and then you have a capacity tier that's more of usually a SAS infrastructure at least, and then either a SATA or SAS, spinning disk capacity tier. So those two different options are definitely still being used in many places, many new deployments, and really it comes down to the cost of the capacity that you need is usually the big factor there. So
there's a couple of questions for you, Jeremiah, on this one, and I think Patrick just answered one of them. So I'll go ahead and be the de facto questioner for because you were doing the talking. So that the SAS interface, is it going to change from 24 gig SAS to 24 gig plus SAS? Is it still 29 pin count SAS?
For the speeds and feeds, there is no change from 24 gig SAS to 24G plus. It's mainly focusing on feature innovations on the media side and feature-wise to be more efficient from a storage architecture. There hasn't been a very big demand to go to a 48 gig, for example, next step speeds and feeds on SAS just yet. So we're refocusing on the media innovation and feature innovation at this time.
Cool. Thank you.
And it looks like there's another question here. Are any of the major storage OEMs using 24G on the back end? So there's quite a bit of 24G deployment already. Several are already deployed in a standard data center implementation, and a lot of AI is using existing infrastructure as it is, because it's already in an installed base. It's known, and you just connect your AI infrastructure to that storage, because ultimately you're farming either existing storage or the attempt to collect a new round of data set that will be installed on a more of a colder tier, warm tier that is still predominantly SATA hard drives on the SAS infrastructure, aggregating to 24 gig on the back end. Sure. Okay. As we transition here, we have some AI storage architecture and problems to be solved, and I would like to open it up to Dr. J here and ask what differences are you seeing for storage between models, and what are the key pain points for storage in AI workloads?
Yeah, and that's the reason why we started off the conversation with the flow of work, right? The packet walk is a bit complicated when you start to look at what the AI workload actually has. As we go through the ingest and we go through the preparation and the training, there are different types of requirements that we have along the way. What's really kind of important is that we create different networks for AI, we create different types of environments for AI, and that means that the access into the data storage itself has to be properly tuned for that purpose. Now, where things get to be really interesting, or or complicated, depending upon how you want to look at it, is that the collision course between what we consider to be memory and storage has been well underway for quite a while. Now, the trouble is that when you actually take the storage, the data from a at rest capacity and format, you need to put it into the memory. You need to transform the data. It just doesn't happen natively. You just don't grab the data off of a drive and use it to process. It's got to go through a bunch of processes of preparation, of cleaning, and that could entail what we normally would consider to be typical data center workloads, like decompression, decryption, and those sorts of things. But it also has to do with data structure formatting. So this requires an ever increasing amount of memory bandwidth, as well as in memory capacity. And as we get into these really large models, and not all models are created equal, by the way, as we get into these really large models, you start to have this kind of a swapping function inside of an AI network. That means that you need to be able to have the proper data where it has to be at the right time. And that's not a trivial function. That means that the data itself, the storage itself, has to be properly tuned to be able to work for these particular types. Now, as we'll see, not all of these different types of processes require the same type of processor. In other words, we could use accelerators like TPUs or GPUs, and we can use CPUs for some types of workloads. But we use data differently depending upon the processor type, which means that if you want to have the instantaneous data access, right, and we're talking petabytes or exabytes of data at any given point in time, you got to be able to put it in the right format, because we use these things differently, whether they're serial or parallel. So that means that the data isn't always going to be where it needs to be when it needs to be. So you're going to get these intermittent data surges that go along with the nature of that workload. Some of these happen to have a very strong write cycles. Some of them have very strong read cycles. Some of them are random. Some of them are serial. And so different types of storage and different types of storage access are going to be needed in order to make this the most efficient. As we saw inside of the poll earlier, if you want to have good performance, that means you actually have to have the data in hand. So you can't do anything unless you actually get the processing data itself. Now, the other part of the problem that is kind of unique to this type of workload is that these operations wind up being rather long term. They could be hours, days, even weeks. So what winds up happening is that if you've got the different types of accelerators, like so let's just say you have a GPU, and you need to be able to share that information amongst different types of GPUs, and you don't have the amount of memory bandwidth that you've got to be able to hold that data. You have to be able to go out to the data often to be able to pull it in. That's where the direct access comes in handy. That's where the localized storage comes in handy. But they all come with trade-offs, and understanding those trade-offs are important, because the actual workload itself is dependent upon the last bit back. In other words, if I've got a GPU and I've got to communicate with other GPUs, I need to make sure that I have the last bit coming back from all those different GPUs which do the processing depending upon the workload requirement itself. And I can't actually call the workload completed until I get that back. That's what we call tail latency. And it is incredibly important in an AI workload, because of the fact, where I should say AI workloads, there are multiple different subsets of this category. And this means that the actual monster of AI itself has to be accommodated when we start talking about the data and the processor and how it actually works together. So what we showed before in the previous slide with regards to the stripping down of the preparation, the ingestion, and so on, it really breaks down into a lot of multiple different types of workloads. What it really looks like is far more complicated than people realize. It's not just simply about passing things through on a conveyor belt. And so once we start to talk about ingesting, we're talking about high capacity and the sequential write performance of bringing in from multiple different sources. They could be scraping of web data. It could be databases. It could be automotive. It could be a number of different areas. But the actual content itself, which comes in its own different form, has to be ingested inside of some system where it can then therefore be prepped. And that means that we've got sequential read and write performance that has to be handled, which is a little less of a capacity issue, but a lot of reads and writes. And then as it goes into the training format, which is a churn of data that goes through a number of different processes and other different forms, you've got a lot of random read performance, a lot of of high read and write at various different stages along the way. And this is a process that involves going back and forth as we go through the different passes and where it actually winds up getting stored, because that winds up being a very delicate process. And if you've read any of the white papers that have been done by Microsoft or Google or Meta, you start to realize it's not a trivial scenario, because you have to make sure that the work that you do gets gated by a function that allows us to be able to say that if something goes wrong, we can go back to that particular checkpoint. And that's what we actually call the checkpointing. Checkpointing isn't just writing data to a storage place, although that's one of the functions that it does, but it is an incredibly important and nuanced faction that the storage community needs to be able to understand. Checkpointing isn't just about saving your state. It's not like you're going to auto-save in your Word document. It's much more involved and much more complex than that. So checkpointing is an art form in and of itself that is directly tied and intimately related to what we do in terms of storage. And then later on, after we get into the whole idea of where we get into the trained model, now we have to generate the actual material. If you go into your ChatGPT or your Grok or any of these other kinds of interfaces with the human beings, you need to be able to generate those responses. That's the inference part of what we're looking to do. Now, that's a lot of random read-write performance as the queries go back in and the tokens are created to generate the responses. And that depends on what kind of model you're doing too, like a reference model. Like you go on to your online shopping and say, customers have, like you who have looked at this also wind up buying this, or they also wind up looking at that. That reference architecture, that's non-trivial, but that's the part of the process that involves a lot of random read-write performance from a storage perspective. And then, of course, you've got the archiving, which is probably the most familiar to storage people. You've got a really high capacity, and you've got the ability, you have the need to be able to, to generate that material out. There's a lot of sequential writes, but it's a heavy read that goes into that particular process as well. And each and every one of these stages constitutes what we consider to be an AI workload. And it's not a one-off. This actually churns all the time. That archiving then winds up becoming part of something else that gets ingested in the future. So these circles within circles within circles and these looping functions are heavily involved in different types of storage at different types of requirements. And that allows us the ability to tailor the storage environment at any given point in time to the performance that are required to then ultimately wind up with the better ROI. So all of these things wind up kind of working together. So let's go back really quickly and take a look at this high-level overview and identify exactly the kinds of things that are being done to facilitate these things from a SNIA perspective, right? So what we do inside of SNIA is we try to augment these different elements at different places to help identify certain aspects of what it is that we're trying to accomplish. So if we're talking about the proper placement of data on the ingest, we have something that we're working with the NVM Express group on storage data placement to be able to most accurately place the data where it needs to be, when it needs to be, so that you don't have an awful lot of round tripping. From a memory perspective, we have something called SDXI, which is a Smart Data Accelerator Interface, which allows you to effectively use the hardware of a processor to move data from one memory region to another memory region. It is a way of helping facilitate the movement of data without having to go through several abstraction layers that wind up doing the transformation of data to be able to have one form of a workload be able to use another workflow. Wow, say that 4 times fast. Then, of course, at the physical layer, we've got SFF, right? We've got the connectors, transceivers, and form factors that will actually facilitate the interconnects between these different component parts. Of course, we've got STAY, which is what you're listening to right now. And then we've got the NVMe over Fabrics driver specs, as well as for where a lot of the future work is coming in from DNA-based storage, which will have to be used for ingesting to be able to be processed and trained based upon the way that new form factor is going to be, or data structure is going to be processed. And that's just in the ingest part. On the transformation part, we've got the computational storage work that's going on that allows you to do the processing near the data itself. So one of the things that has been very useful in some of the government labs has been the ability to do the processing to properly prepare the data at the source location itself. And then, of course, that allows us to be able to use the memory to memory transfer inside of the processor to be able to handle this transformation before it has to get transported. The reason why we do this is that the best I/O is the one we never have to have in the first place. So if you can create the data transformation where the data actually exists, as opposed to sending it over a network, that reduces the tail latency time considerably. And then we get into the actual training and tuning itself, which has all of these different things we've been talking about so far. We've got the computational storage, we've got the DPUs, but we've also got the ability to do this in an efficient manner. So we've got work being done inside of the green storage and energy groups to be able to handle the efficiency aspect, which reduces the power, reduces the cooling, reduces that total cost of ownership, and the return, and increases the return on the investment. And then, of course, at the inference and tuning part, where we actually have the processing where we want it to be, well, of course, we continue to use the abilities that we've been talking about so far. And these are just high-level views that we're looking to do inside of SNIA, and we're always working on new projects to be able to handle more and in improved efficiency ways of making this kind of workload or sets of workloads be more efficient and less time-consuming. So what we're looking to do from a storage AI needs is we want to improve the scalability and the performance. Did I hit? Oh, okay. Whew. I thought I hit something. We want to improve the scalability and performance because the scale out architectures wind up having more and more taxation on the ability to move the data from one location to another. So if we can reduce that tax on the movement of data, the better off we're going to be. And then, of course, we've got the different structure types of data diversity that happen at the edge, all the things that we're talking about with those different data sources, your phone, your car, your DNA storage in the future, all of these different things that require thought processes now. And so that in turn means, where is it going to come from? Well, the cloud integration process, so the ability to do proper, object storage requirements, then how they wind up becoming more fluid inside of the AI workload. How does that wind up reducing the amount of cost? And so it goes back to the ROI and the TOE. How does software-defined storage actually allow us to be able to facilitate the management structure that goes along with being able to do this? How do we handle this from a server perspective, from a rack perspective, from a row perspective, from a data center perspective? All of these different things have hierarchies of an approach, and maybe even a fractal approach, because of the fact that it winds up becoming far more fluid and integrated as we move along. And all of these things lead into AI specific features, the GPU integration, the TPU integration, the ability for the memory to be able to have more native access into the data capacity itself. All of these different things, it's not just about what the transport is like or what the capacity is like. All of these different systems are really integrated and tightly integrated, and the margin for error becomes much, much smaller, right? So we're no longer talking milliseconds of latency where we can kind of finagle and futz our way through this. We're talking nanoseconds of latency. And that becomes incredibly important. The margin for error is really, really small. And so if you've got to wipe out something and start all over again, it winds up being a much bigger hit than what we would probably have considered maybe 10 years ago. So before I move on any further, Patrick, did you have any thoughts about this? Because I know I kind of blitzed through a whole bunch of stuff.
No, I love it. I think the other big ones though, just and you have them in here, but when we talk about scalability, right? Just give you something. I got to tour El Capitan, which is the largest, number one on the top 500 list, Department of Energy supercomputer this year. So I got to do it like the day before it went and started its classified mission in January, and that was it was like 40 something thousand accelerator system. So it was an AMD MI300A based system. And when we start talking about AI clusters today, we're talking about, probably large scale AI clusters are now into the 100,000 plus GPUs each, and you have 2 CPUs for that. You have a number of NICs, each of these systems and a lot of these components have drives attached to them. Then there's huge, many exabytes of storage attached to them. So from the standpoint of power, power becomes a huge constraint on anything. And also reliability is something that, as folks operate at a new level of scale with a new level of like numbers of nodes under one building, and all operating at a high speed, I think the reliability standpoint reliability discussion is one that I've heard a lot in the last probably couple months. So
yeah, it's all consistent with what I've heard too. Okay, so thank you very much for that.
What I was just going to ask here, what are some of the innovations that we're seeing on the AI infrastructure side? Looks like memory is one of those.
Ask and ye shall receive, my friend. Congratulations, and the check is in the mail. Thank you very much for setting me up that well. That's a beautiful set. I'm ready to spike this puppy right now. So obviously what I was talking about before with regards to the intersection between memory and storage is a key component for what we're looking to do in now and in the future, right? So one of the things that we're trying to figure out is how do we get the processing closer to the data, not just the data closer to the processors. So what this means is that we're trying to figure out, especially at SNIA, we're trying to figure out how do we handle the approaches for fabric attached memory. Now, obviously, there are organizations like CXL that are dealing with memory pooling and memory extension, and we're trying to work very closely with other organizations that are dealing with memory in that regard. And so how do we deal with these hierarchical memory pools that go along with these kinds of things? Because every single time you add in this actually goes to a question that came in not too long ago with regards to tail latency, right? So remember that we're talking about individual systems that have to work together to be able to solve a much bigger problem. So if I've got a system of a GPU and CPU, because they go together, if I got a CPU GPU system and there's an awful lot of round tripping that goes back and forth between those two processor types and those different memory types, and I've got different memory hierarchies, and those memory hierarchies have different latencies and different latency budgets to do different types of work, and I have to go back and forth and chain up and down that stack. And then I have to go talk to another set of CPUs and GPUs and memory hierarchies, and I've got to communicate between those, and I've got to do this in a cluster, and I have to do this across a network. All of these different things require additional computation of the latency that brings back for each and every component part of a workload. So if I've got a set of workloads that require an all reduce or an all to all, where all the different data has to be collected from all the different GPUs or CPUs, or if I've got to be able to have all that different data collected to one GPU or one CPU, that's where that last bit back comes into play. If I have to deal with the pachinko chips that go through all of these different memory hierarchies, I want to make sure that I have the least amount of interference for each and every one of these so that that last bit gets back very, very fast. And that means that the interprocessor network for the fabric endpoints, whether they be in a scale-up fashion or a scale-out fashion, have to be tuned properly to get the data correctly back. And then we have to deal with how are we going to handle this through, different types of access, right? Is this going to be Ethernet-based, storage data? How are we going to get the network to work with the storage itself to be able to facilitate this? Because remember, we are talking about dedicated networks specifically for AI. What do we want to do? Well, what we really want to do is we want to make sure that we don't have to round trip out to an open, generic front-end network like we currently do in order to get the best possible performance for these very tightly coupled systems. So understanding what the networks are with regards to how the workload is compared to other systems is going to be really important, and one of the things that we're trying to do inside of these various organizations, SNIA included. And then, of course, we've got the low-level efficiency improvements that we're talking about. Jeremiah talked about, how the GPUs and the CPUs can be used properly to directly communicate with the data itself on the drives. How do we deal with the process of mutating the data and restructuring the data inside of the storage units themselves so that we don't actually have to do a whole bunch of round tripping between the processor and the data types. So these become very critical components of what we're looking to do. And so that's what SNIA is looking to do. And this is kind of a summary of that particular approach, where the SNIA work that we're doing covers all of the stuff for driving the data itself, the data management. We've got the new functions and features that we're trying to accomplish, things like the DNA data storage. And then we're also looking for policy procedures that are going to be AI friendly for these kind of specific workloads. Rather than a generic workload where all storage is going to be accessible by a host, and you got this client server type of approach, it's much more of a peer-to-peer kind of a thing for AI, and that means that we have to start thinking in different terms of a producer-consumer type of a form. And then finally, just the last kind of thing to make. We know that we're doing some pretty smart stuff, but we're also smart enough to know that we're not smart enough to know everything. And so what SNIA is doing is working very closely with a number of different organizations inside of the industry to be able to couple the work that we're doing and not work at cross purposes. And this includes groups, but not limited to, the Green Grid, DMTF, CXL, Ultra Ethernet, NVM Express, and more. And so we've got a whole bunch of other alliances that were in the works, and we're going to be working with these other organizations, and they're going to be working with us for everything from 400 gig per lane Ethernet to data, near data compute. We've got a whole bunch of stuff we're working towards in the future, and that's ultimately what we're going to be trying to do, is create an industry-wide solution to a very complex and ambitious problem. All right, so back to you, Jeremiah.
Great, thank you. So as we get kicked over to the next topic here, just wanted to kick off a polling question about which aspect of storage for AI workloads is most critical. So I'll go ahead and turn on that poll, and as we get started into the next portion, people can respond, and we'll talk about the results as we're moving along here. So as we continue our discussion here, wanted to take a look at the real world insights. And Patrick, I wanted to give you a chance to talk here and let us know, some of the amazing data centers and some of the things you've seen that are focused on AI, and how do you see compute and storage evolving for AI? Talking about the architectures, and give us an overview of what you're seeing in the real world, if you don't mind.
Yeah. So Are we gonna go to my slides first, or do you want me to just talk about it?
Yeah, go ahead, and you can jump in, and we'll address the poll as you're going along.
Awesome. Hey guys, so I have the best job in the world. Let's just call it what it is. I get to go and take apart server storage networking gear for a living. I get to go out to different places in the world where people assemble everything from pretty small environments to very, very large environments, where you're starting to see 5, 10, even, many more billions of dollars of hardware under a single roof. I think some of the things that, I like to start with are always the building blocks, right? And I kind of start with this as just kind of the AI servers and local storage, because this is the one that I think a lot of folks ask about, and it's very tangible to folks. And so these are just a handful of servers over that we've either published recently reviews on. We have the NVIDIA NVL70 GB200 NVL72 there, which I think we actually took that photo about a year ago. But then we have a number of other systems that either will go live, like the one in the bottom left is probably going to be a video that's going to go live tomorrow. We have a Supermicro one. We have all different systems. But one of the kind of things that you'll notice immediately is, this is an STA SNIA presentation, and the architecture in servers in general these days, in AI servers, tends to be very focused on NVMe storage. And that's just kind of, there are a number of reasons for that. The primary one is just the goal inside a server is just to go as fast as possible. And so, and really to fill each IO lane as much and as often as you possibly can. And that's the reason we see that. There are still some servers where you have provisions for, say SAS or SATA built in, but those tend to be, tend to be a little bit less. So I guess, the number one question I would get, or I would think about if I were attending this would be, well, if it tends to be an NVMe dominated world inside the actual compute servers, why are they talking about this here? And so really that's want to take a step back, right? So the storage that you have in a local AI server tends to be very fast, but it also is limited in capacity. You have a number of drive bays, but you don't have unlimited drive bays by any means. And all of those PCIe lanes that you use for things like storage, they also are competing with NICs, they're competing with GPUs and other devices in the system, and PCIe lanes are not an unlimited resource. So at some point, you obviously need to go access exabytes of data for high-end AI training. And when you do that, you kind of need to just go outside of that box. And so really, I talked about this a little bit earlier, and I mentioned I had a slide on it. There are really two camps, and there's a number of different ways you can make this a lot more complex, but there are two camps essentially when it comes to that shared storage. The first camp I see is really folks doing all flash. There's a number of vendors really focused on all flash that have done very well in the AI space recently. That could mean that they're using QLC NAND, could mean that they're using all different types of NAND in their systems. And in the all flash systems, you tend to see those are NVMe dominated. Where you do tend to see more SAS though is really in the mixed or the tiered one, right? Where you have some flash up front, which is really providing that fast access. But then on the back end, you have disk for that high capacity at a relatively low cost. When you look at that disk-based architecture, like, the end of the day is the way that you build that disk-based architecture is that at minimum, you have a SAS infrastructure with SAS expanders and controllers and stuff. And then you put drives in that are usually either SATA or SAS, right? But at the end of the day, the infrastructure for that disk-based part is currently SAS. Now, one of the challenges folks have is, of course, a lot of times the disk model looks very attractive when it comes to a price per, terabyte, petabyte, exabyte stored. But on the flip side, there's always the question of, power in a data center, and I think that's usually a pretty big one. And then also, there's really interesting things like when you get into these large clusters, like for example, if you use like the really high capacity NVMe SSDs, you can fit higher density into your racks. And therefore, things like the runs for your optical connections between the different parts of your AI cluster can be shorter, and you can save money on optics if you can actually fit your storage into a smaller footprint. So I guess it's an interesting way to just say, the first order things that we think of are always the costs associated with the physical media, with the boxes that they go in, with the clustering, with whatever we need to go and create these large storage solutions. But on the other hand, there are other costs when you start getting into the AI realm that aren't even captured in those in those metrics, because you have so much interconnect that's in an AI cluster that you just, at some point, yeah, things change just based on that. And that has been pushing folks to look at this in a, I guess, a more careful way. So kind of going to the next part is like where is data today? And the picture that's in the corner, I think, is super important. So if you think about where data is today, we're going to leave the highest end AI clusters, right? The 100,000, we'll call them the 100,000 plus AI accelerator clusters. We're going to kind of leave those for a second. But if you think about like where a lot of the data is today, right? We have a lot of data if you're an enterprise in, say, your enterprise storage arrays that have been around for many, many years. A lot of folks have stuff in cloud storage. There's stuff in local storage, whether that's in someone's laptop, whether that's in a embedded PC that's in a factory, whether that's even in a data center, you have local storage on and you have people that store things locally there, and then backup storage, right? And so the interesting thing about this is that the vast majority of those systems could support a relatively small AI cluster. Cloud storage is definitely one where there are ways to go and access very large cloud training solutions. But a lot of folks, frankly, are running into a issue right now where if you're an enterprise, where you have your data is not necessarily where your AI servers are. And that's been a really interesting thing that as I've been talking to companies, we do consultations all the time, but one of the big ones is like, I have these giant, NetApp arrays or Dell EMC arrays or whoever's arrays. Probably not supposed to say vendors, but we have these old legacy arrays. We want to go do AI, but the challenge that we have is, number one, are those fast enough to do what we need? And often they're not. But the second issue is that when they are looking at how do we go build an AI cluster, the big question is, how do you get enough power to go run a sizable AI cluster that's not just a couple machines? A couple machines you can probably fit into an existing data center footprint by doing things like swapping out to newer generation CPUs and redoing your virtualization cluster, get a little power back there, and you can do a small AI cluster. But if you're talking about a sizable AI cluster, you're starting to need megawatts of power that folks just don't have. And so the obvious choice is, okay, well, now we got to go find a new data center, new co-location facility, whatever it is. And when we do that, we are going to go build our AI cluster there. Great. But now your data is sitting in a data center somewhere else. You don't have a fast enough pipe to feed a giant AI cluster. And that's just on the data center side. Once you get to people's laptops and local storage and all that, it gets even worse. You may not even have enough bandwidth to the cloud to make that a interesting conversation at this point, right? So I think that the proximity of data to the AI accelerators pushes folks to really look at an AI specific storage solution for anything that's. I've definitely seen some smaller AI clusters that are using existing solutions, but most folks are building new AI storage solutions just for that. I also, it kind of leads me into what that bottom photo is. So that is a NVIDIA ConnectX 7 NIC. So it's a 400 gig port on there. It's kind of funny, but when you think about how much a 400 gig link is, and this, by the way, is if you go look at large AI clusters, most of them are using 400 gig Ethernet. The switches right now are 51.2 terabit switches. So they split each of the ports, the 64 ports are into two. You get 128 ports of 400 gig, or you can have uplinks and all that kind of stuff. But the big thing on this is that you have 400 gigabits per second, which is essentially roughly equivalent to a PCIe Gen 5 by 16 slot. So if you just kind of go into that, you have 4 PCIe Gen 5 NVMe SSDs that you probably need at minimum to be able to saturate this thing. But if you were to go back to the generation or 2 generations old servers, you're talking about the vast majority of the world was deploying in 2017, 2019, all the way up until 2021, the Intel Xeon Scalable, right? And so Xeon Scalable Cascade Lake, I've heard some people say it's like 40, 50% of the installed base. It's this crazy number just because they were sold for so long. And in those servers, you had, I think it was like 48 PCIe Gen 3 lanes, right? So all of the IO out of a server CPU that's in the vast majority of the installed base, which is, everything from your virtualization servers all the way to the storage arrays, they literally can't, they cannot from one CPU push data fast enough to saturate a NIC that comes out of an AI server. And oh, by the way, each GPU in an 8 GPU server will have its own NIC, and you probably have 1 or 2 additional NICs, one either shared by the 2 CPUs in that server or for each CPU, right? So the you're talking about, it's not uncommon to see a AI server today with 4 terabits per second of interconnect bandwidth each. And so when we talk about storage and high performance storage, I think one of the interesting things is, the AI folks think about it in a vastly different way than a lot of legacy storage has been done in the past, right? Because it is all about feeding those GPUs as fast as you possibly can and keeping those compute units busy. So we talked about tail latency just a little bit ago, and that tail latency is another really good example, right? Where if something is waiting for a storage transaction that somehow slows that one GPU could be slowing down its 100,000 or 99,999 other GPUs and preventing those from doing work. So it's so the interconnect side is just absolutely fascinating when we talk about not only where is data today, but some of the challenges that folks are running into on the AI side.
Yeah, and I think that's where the polling question, kind of resonates with that, where the AI workloads are most critical is on the speed front, and you're certainly servicing that and needing that on that infrastructure.
Yeah.
Capacity and cost and reliability are secondary concerns, although not, lesser important. They're just, the focus right now is all about speed, because you can't seem to feed things fast enough to the AI modeling, right?
Well, there's also the additional nuance of the fact that speed is the amount of work you can do between errors, right?
Right.
So one of the big problems that you've got is that most of the failures that occur inside of a workload are often physical in nature, right? You have a cable or you have a transceiver or something, because we're talking hundreds or tens or hundreds of thousands of these things, in the workload. So the percentage or the chance of probability, that's what I'm looking for, of an error occurring in a short period of time goes to 1. And so you want to have a really good high performance system, because you can get to the checkpoint area quicker and more reliably to help avoid those kinds of regurgitation of the workload going back to a gated point. So the performance is more than just making sure you get the workload done. It has to do with reducing the amount of impacts on the errors.
Awesome.
All right. Well, as you wrap up here, Patrick, we can finish up with some opportunities and challenges, and let's see where we end up.
I'm just going to go real quick. One big thing that we're going to talk about a little bit this weekend in the newsletter is kind of really, what is a storage for AI agents and what do the AI agents look like? We've talked a lot about training clusters and some of the large inference clusters, but there's a question on what an agent looks like. How is an agent embodied? And I think we're going to hear a little bit more about that next week, especially. So we'll talk a little about that. But if the units of compute are different, instead of 100,000 plus accelerator systems, we're talking about a small system and a bunch of them, that all of a sudden looks different in terms of storage. And then I know we're kind of short on time, but the other big one was just really, where does data land in a couple of years? This is very much a discussion that was going to be very similar to what we had, but also just kind of when you have AI generated data, people right now are talking about feeding the AI systems, but when it starts to become inference dominated, what you'll see is the systems are going to start generating so much data. We're talking about LLMs and text right now, but as you start getting more and more into, video generation, what do you do with that from a standpoint of when machines can just create an arbitrary amount of video, and you need to maintain that video for compliance purposes or for other purposes? There's a huge amount of data that's going to hit the capacity tier based on that machine-driven, AI inference push that we're not too far from. So that was my last one there.
All right. Well, thank you. I'd like to thank you guys for joining us here today. If you have some parting thoughts or messaging that you would give the community here on next innovations and the implementation storage, whatnot, I would like to give you an opportunity to close out here, and appreciate your time. Thanks for joining us today.
Well, the only thing I would like to say is that, as you can see, there's an awful lot of work to be done. There's a lot of requirements for people to have their voice heard, and we are always looking for people to join and work with us at SNIA. So please do reach out to us at SNIA and lend your voice. Patrick?
Awesome.
Thank you, Dr. Shea. Yep.
Yeah, and if anybody has any questions or what have you, we're gonna have a lot of content on this over the next 2 weeks. And then also, and that'll be both on the STH main site, which you can find a link in the slide there, as well as our YouTube channel. If you haven't subscribed yet, we're hoping to hit 1 million subs by July or so. So, if you haven't subscribed, it'd be awesome if you could. That's my little plug. So,
great, thank you. And once again, I'd like to thank everyone for joining us today. Just a reminder, SaaS technology will keep evolving and innovating with new features and capabilities to address AI storage needs. 24G Plus has some that will help but the T10 that creates the specs will help ensure necessary capabilities will be developed that will keep SaaS a part of the world of AI. So, just like to thank everyone for joining here. Here's a link to SNIA. You can, and the Stay Forum, Stay Community, and our social messaging links as well. Thank you again. Take care, everyone.
Awesome. Thank you.